start a new topic of vector spaces. Any questions? Okay, so let's begin a new chapter on vector spaces. Okay, this is so far we were dealing with matrices and the row vectors and column vectors and doing some hand computation and Gauss elimination. These are computational methods, but now we rise to a new level. It is a abstract level. Okay, it is an abstract level, but to understand all the nitty-gritties of solving linear equations, we need to understand the totality of all vectors, uh, rather than just do computations with a bunch of vectors. We have to understand the space in which all the vectors live. Okay? What are the algebraic properties of that space? What are the geometric properties of that space? And understanding the space of all solutions of a system of homogeneous linear equations or the space of all vectors, yeah, it gives better insight into solutions of a given system of linear equations. So our ultimate purpose in linear algebra is to solve system of linear equations. All the problems which deal with applications, uh, they uh, they give rise to non-linear equations many times, very often, but these non-linear equations are converted into linear equations. We just look at the linear part. And for many applications, just the linear parts of non-linear equations are enough to solve for many problems in arising in applications. And you will see that the linearization method is a very, very efficient method. So these non-linear problems which arise in nature, they are converted into linear problems, but the linear problems amount to solving a system of linear equations. And then we have to understand the qualitative nature of the system of linear equations before we start computing the solutions. So methods of computations, there are many methods of computations. We have learned the Gauss elimination method, but there are many variations on these which are more efficient if I know the coefficient matrix. Yeah. So the Gauss elimination method works on any matrix. Okay. But if I know the structure of the matrix, then there are better methods for solving system of linear equations. But now in this chapter, we study basics of vector space theory, and we will see that it gives better insight into the nature of a coefficient matrix and the nature of solutions of given system of linear equations. Yeah. So the equation ax equal to b, where x is consisting of n indeterminates. As I said, it can be viewed in this way, that ax is really the linear combination of the column vectors of A. Think about ax as x1 times first column vector plus x2 times second column vector plus xn times last column vector, and that is equal to b. So it says that the given system ax equal to b, okay, it has solutions if and only if b is a linear combination of the column vectors. Otherwise, it will have no solution. So the left-hand side of this equation is indicating that we should actually look at all possible linear combinations of given set of column vectors. So the system of linear equations give rise to matrix equation ax equal to b, and the given matrix has the n column vectors, yeah, the n column vectors, and to see whether there is a solution, okay, we look at the space of all linear combinations of n column vectors. So xi's are indeterminates. So I will give different values to xi's, okay, and get all possible linear combinations of ai's. That is certain space, okay, and the solubility of ax equal to b says that the vector b lies in that space, okay. So this is AI is the ith column vector, and the left hand side is varying over linear combinations of all the column vectors of A. This gives rise to the idea of vector spaces. Okay. So to say that ax equal to b has a solution is equivalent to the statement that b is a linear combination of column vectors of A, and we shall now look at the spaces of linear combination of vectors for a deeper understanding of system of linear equations and matrices. Yeah. So we will define the fundamental notion in linear algebra, that of a vector space. And you have seen vector spaces already in calculus. And the vector space that you saw in calculus was Rn. Yeah? And so points are in Rn, and we calculate many multivariate functions at points of Rn. But Rn can be thought of as the space of linear combinations of n column vectors, which are the basic column vectors. Yeah, right? Rn is simply the set of all linear combination of basic column vectors, where xi's are some real numbers. Okay. Yeah. So to solve the matrix equation, we are also looking at linear combination of column vectors of A. But if we take the basic column vectors E1 up to En, then this set of all possible linear combination is nothing but our usual n-dimensional space Rn. We will define dimension little later, but you understand intuitively what is the dimension. Dimension of R2 is 2, dimension of R is 1, R3 is the three-dimensional usual three-dimensional space in which we live, but we will make the notion of dimension precisely. This is one of the purposes of introducing vector spaces, that we want to capture the notion of dimension precisely algebraically in terms of linear combinations. Okay. So non-empty set of objects, this is the definition of vector space. A non-empty set of objects called elements or vectors is called a vector space over the scalars f. The scalars could be the set of real numbers, or they could be set of complex numbers, or they could be set of the rational numbers. Okay. So we are dealing with these three fields. In applications, there are analogs of these fields which consist of finitely many numbers. For example, in computer science, we deal with binary system. So the set consisting of 0 and 1 is also a field, and it can take place of R or C. We can do all the linear algebra over the binary system of real numbers. Yeah, and that's what is happening in actual computer program. All information is converted to zeros and ones, and we are doing arithmetic modulo 2. Doing arithmetical modulo 2 is really doing vector space theory over the field of scalars, which is consisting of two elements. So linear algebra can be done over a variety of fields, field of real numbers, field of complex numbers, or finite fields like the binary system of numbers 0 and 1. There are similar binary systems, similar systems of numbers which have prime number of elements. So these are called integers modulo p. Okay. So much of linear algebra that we do in this course is actually applicable to a set of scalars which are either field of real numbers or complex numbers or a finite field. Okay. So a non-empty set of objects whose elements will be called as elements or vectors, although they may not look like vectors, is called a vector space if this list of axioms are satisfied. So there are 10 axioms for a vector space. Don't be scared of the number of axioms, because you have seen all of them before. Since high school time, you have actually seen these axioms. But now we are putting all of them together to make a algebraic object called a vector space. Okay. So first set of axioms are called the closure axioms. So closure axioms, the closure axioms are for every pair of elements x and y in V. So elements of V we are calling as elements or vectors. Yeah, both the terms are used. So to take two vectors, then there's a unique vector called x plus y. This is called the sum. So in the definition of vector space, we are not specifying how we are going to add the vectors. If it is Rn, we know how we are adding. We are adding vectors component-wise. But in definition of abstract vector space, we are not specifying how we add the vectors. What is important is the properties of this addition. Okay. So repeatedly we use these properties, and these properties are satisfied in many cases. So we abstract them in terms of axioms. So these are the closure axioms. The first closure axiom that deals with addition of vectors. Okay. So for every pair, there is x and y in V. There is a unique vector called x plus y. Okay? And for every x in V and for every scalar, there is a unique element alpha times x. This is called the scaled. We are scaling the vector by alpha. Alpha is a scalar. It can be real number, it can be complex number, it can vary over the finite field. But when we define a vector space, we fix our set of scalars. Okay, so F is that set of scalars, and the second closure property says that for every alpha and for every x, there is a unique vector which is written as alpha times x. This is called the product of alpha and x. We are not specifying how we are arriving at alpha times x, but we are specifying that this is called scalar multiplication. The first operation is called the addition. So we have these two operations in a vector space. These two operations satisfy certain axioms. These are the axioms for vector addition. Yeah? There are 4 axioms for vector addition. First is that vector addition is commutative. The second is that the vector addition is associative. Then there is a 0 element for addition of vectors. X plus 0 equal to 0 plus x equal to x for all x. The fourth axiom says that for every x, there is a negative of x, so that when you add the negative of x to x, I get the 0 vector. Okay, so these 4 properties you are familiar in the n-dimensional vector space, namely Rn. Okay, so elements of Rn are column vectors or row vectors, and we have a component-wise addition, and we have component-wise scalar multiplication. And these 2 operations in Rn, they satisfy the 4 axioms for vector addition. Okay, these 4 are also true for real numbers. These are extracted. These 4 properties are extracted from the set of real numbers. In real numbers, we have addition and we have multiplication. So ignore the multiplication for the time being. Then just look at the addition of real numbers. Then these 4 properties, that is commutativity, associativity, existence of 0 element, and existence of minus x. Minus x is called the additive inverse of x. When you add the additive inverse of x to x, I get the 0 vector. Okay, so these 4 axioms, they are stated in this sequence. The sequence is very important. Yeah. So I have to first introduce this 0 element so that I can talk about additive inverse, because additive inverse involves the 0 element. Then these are 2 structural properties, that addition is commutative, addition is associative. So these are the 4 axioms for vector addition. Then we have similar axioms for scalar multiplication. So first is the associativity. Alpha times beta x is alpha beta times x. This is the scalar product of scalar and a vector. Yeah, x is a vector and alpha and beta are scalars. Then alpha times beta x is same as alpha beta times x. These are obvious for this usual space in which we operate. These are obvious because multiplication of real numbers is associative operation, but that translates into this axiom for scalar multiplication, associativity of scalar multiplication. Then so we have these 2 operations, addition and scalar multiplication. They interact with each other. So scalar multiple of alpha x plus y is the sum of alpha x and alpha y. Okay. Whether you first add the vectors, then take the scaled version, that is same as scaling the 2 vectors simultaneously and then adding them. Then existence of identity. So one is a scalar. Yeah, the scalars are either real numbers or complex numbers or a finite field. Then the multiplicative identity is there in those fields. So take 1, which is a scalar, times any vector, and that is equal to x. We have to specify that 1 times x is x. Okay. Distributive law of addition. So add these scalars. Here we added the vectors and multiplied by a scalar. Here we are adding the scalars and multiplying by a vector. I get alpha x plus beta x. Okay. So these are 4 axioms for scalar multiplication and 4 axioms for vector addition. Okay. Yeah. So any set of vectors with these 2 operations of addition of vectors and scalar multiplication which satisfies these 8 axioms is called a vector space. When f is equal to r, we say V is a real vector space. If f equal to c, then V is called a complex vector space. Okay. So we will come across real vector spaces and complex vector spaces. Even in applications, we have to understand the complex vector spaces. Although in practice we deal with real numbers very often, but in fields like electrical engineering, you will see that complex numbers are used very often. So, and in computer science, finite fields are used very often. So, as the field of scalars is varying, the nomenclature for vector space also varies. So, real vector space when the field of scalars is real numbers, complex vector space when the field of scalars is complex numbers. Yeah. All right. So, are there any questions so far? Okay. So let's look at some examples. There are numerous examples of vector space. The concept of vector space came out after a long time because many sets of vectors or functions or matrices, they behave like vector spaces. They behave like Rn. Okay. So seemingly different objects, they form vector spaces. So let us look at that. Yeah. So take the set of real numbers. V is set of real numbers. The field of scalars is also real numbers with ordinary addition and multiplication as vector addition and scalar multiplication. This gives a real vector space. So the field of real numbers is a real vector space. Yeah, all those 8 axioms are satisfied for addition of real numbers and multiplication of real numbers. We can look at the field of complex numbers and the vector space, which is again the field of complex numbers. So with ordinary addition and multiplication as vector addition, scalar multiplication, this gives a complex vector space. This is a twist. We restrict the field of scalars. Take the vector space of complex numbers, but the scalars are real. Then and it satisfies all the 8 axioms: addition and scalar multiplication, multiplication of complex numbers, satisfies all the 8 axioms. So the field of complex numbers becomes a vector space of real, and it can also be considered as a vector space of over the complexes itself. These two vector spaces have different structure. Okay. Yeah, this is our usual space, Rn, Euclidean space, consisting of either the row vectors for addition and multiplication, which I described, how to add row vectors and column vectors, how to multiply a row vector by a scalar or a column vector by a scalar. So if you think of row vectors of length n, they form this n-dimensional real space, real vector space. Similarly, we define the real vector space of real column vectors. Okay, real column vectors. And depending on the context, Rn can be the vector space of row vectors or column vectors with n real components. So the context will tell you whether Rn is representing the vector space of row vectors or vector space of column vectors. Okay, the same notation will be used. If you want to be really fussy, then this is the space of column vectors with n components, and this is the space of row vectors with n components. But we just write both of them as Rn, and the context will make it clear whether we are looking at row vectors or column vectors. Let's look at some more examples. Look at the row vectors with complex entries, and that becomes a complex vector space with respect to addition of row vectors. Yeah, and then we can similarly define complex vector space of complex vectors with n complex components. And depending on the context, Cn will again refer to either the row vectors or column vectors with n components. Now look at this. This is a very different example than the usual vectors. Yeah? So look at all functions from this closed bounded interval, real valued functions. Okay? These are real valued functions. And take a set of all possible real valued functions. This is a huge set. Okay? All functions that you encounter, yeah, in one variable calculus, they are in this set. It's a huge set. And take this field of scalars to be real numbers. I want to convert the set of all functions into a real vector space, real valued function on closed bounded interval into a real vector space. In order to convert this into a real vector space, I must define addition of functions. I must define scalar multiple of a given function. So this is how we do. So take two functions from V, and then there is sum. Their sum is again a function from AB to R, and we define this f plus g operating on x is simply fx plus gx. Okay. This is how you added functions in calculus, and this is the addition of functions we are taking to convert V into a vector space. How do we do scalar multiplication? Well, take a scalar and take a function, then a times f is another function, but a times f operating on a real number x from this closed bounded interval is equal to a times fx. This is again a function. This is the scalar multiple of f. So we have defined addition of functions. We have defined scalar multiple of a function. And the field of scalars is real. So this is, you can check that the 8 axioms for addition and scalar multiplication, they are satisfied. Okay, they are satisfied. So this becomes a real vector space. And this is denoted by RAB. Right? This is denoted by RAB. In some sense, this is an analog of Rn. Okay, Rn, we have vectors with n components. Okay, they are vectors with n components, and RAB denotes functions from AB to R. Okay, and this is a vector space with respect to the addition. Now let's look at a subset of V. Okay, let's look at subset of V. So polynomials also give rise to real valued functions on the entire real line. Okay, entire real line. So look at polynomials of degree at most n and with real coefficients. This is a polynomial degree at most n with real coefficients. Okay, P and R. And you know how to add polynomials, how to multiply a polynomial by the real number, and these two operations will again convert P and R into a vector space. This is a vector space under usual addition of polynomials and multiplication of real numbers. So polynomials of degree at most n, they form a vector space. I can look at polynomials of any degree also. That's also a vector space. Okay. This is considering all functions, real world functions defined on any closed bounded interval. I can also look at functions defined on the entire real line, functions from R to R, okay, or functions from Rn to R, okay, or functions from Rn to Rm. They all form vector spaces. So it's a very general notion. You have seen many vector spaces without knowing.